Hello everyone, and welcome to video number 10. So we're all done with learning about how to evaluate limits, derivatives, and integrals. So these last three videos of this series will be about applications. And today's application is called the Riemann sum. So the Riemann sum is an application of limits and integrals. And in order to learn about it, you need to remember what definite integrals, which were covered in video 7, are. So here's a recap. Capital F of x means the integral of f of x dx. And if you have capital F of a, where a is a number, then it just means the integral evaluated at x equals a. And here is the definite integral. This is the definition of the definite integral. All right, and here's the fundamental theorem of calculus. So remember that the definite integral can be used to evaluate area under the curve. All right, so now we're getting into the Riemann sum. So suppose you want to find the area under the curve of f of x between x equals 0 and x equals 1. How could you do that? Well, you know from the fundamental theorem of calculus that this area is just equal to the definite integral from 0 to 1 of f of x dx. But there's another way to find the area. So that way is to divide the curve into a number of rectangles, each with equal width, and then increasing the number of rectangles to infinity. All right, so let n represent the number of rectangles. And the total width of the rectangles is 1 because you're evaluating from the interval 0 to 1. And since the rectangles have the same width, the width of each rectangle is 1 over n. All right, so now we want to find the area of each of these rectangles and add them up. So now we need to know the length of each rectangle. The length of the first rectangle is the y coordinate of its top right corner. So this distance right over here is the length, and that's just this y coordinate right over here, the y coordinate of this point. So the x coordinate of the right side, we see that it's a distance of 1 over n from the y-axis. So the x coordinate right here is 1 over n, and that means that the y coordinate is f of 1 over n. So the area of the first rectangle is therefore 1 over n, that was the width, times f of 1 over n. And now the area of the second rectangle, so the width is also 1 over n, but the length this time is f of 2 over n. So the length is just the y coordinate of this point right over here. And you see that the x coordinate is 2 over n because you travel 1 over n to the right 2 times. And then that means that the y coordinate is f of 2 over n. So the area of the second rectangle is therefore 1 over n, which is the width, times f of 2 over n. And continuing this process, you can see that for the third rectangle, the width is also 1 over n, but the length is f of 3 over n because the x coordinate of this point is 3 over n, and that means the y coordinate is f of 3 over n. All right, so the area of the third rectangle is 1 over n times f of 3 over n. And this pattern continues. So the length of the fourth rectangle is f of 4 over n, and then for the fifth, it's 5 over n. And the last rectangle has a length of f of n over n. So we want to calculate the total area of the rectangles. So we add up all of the areas. So that is equal to this right over here. So this is the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle all the way to the area of the nth rectangle. And then notice that all of the terms have a 1 over n, so we can factor that out. So we want to increase the number of rectangles to infinity. So in our formula, n is the number of rectangles. So we want to calculate the limit as n approaches infinity of this series. So now we have two ways to evaluate the area under the curve. The first way was the definite integral, and the second way, as we just saw, is infinite series. So since they both evaluate the same thing, they must be equal. And this is the Riemann sum. So how do you use it? Well, here's an example problem. So this is an infinite series right over here, and you can evaluate it using the Riemann sum. So notice how each term in the problem is equal to the corresponding term in the Riemann sum. So this right over here is the Riemann sum. And notice that the square root of 1 over n is equal to f of 1 over n. The square root of 2 over n is equal to f of 2 over n, and so on and so forth. So we can just consider the first term. So the square root of 1 over n is equal to f of 1 over n. So we want to find f of x, because if we find f of x, then we can evaluate the definite integral and solve for the series. So to find f of x, you replace every occurrence of 1 over n with x. So you see there's a 1 over n here, and there's a 1 over n right over here. So you replace both of them with x, and you've determined that f of x is equal to the square root of x. So now we've found what f of x is, so we can solve for a definite integral. So first of all, the indefinite integral of the square root of x dx, that's just x to the power of 1/2. And by the power rule, you know that that would be equal to x to the power of 3/2 divided by 3/2. And that simplifies to this right over here. And now evaluating the definite integral from 0 to 1, you'll get that the final answer is 2/3. So the value of this series right over here is 2/3. So now, knowing this process,
It's 8 o'clock.
if you want, go ahead and pause the video and try this problem by yourself. And you don't need to evaluate the value of the definite integral. You just need to write it as a definite integral. But anyway, here's the solution. So notice that each term is equal. So ln of 1 over n is equal to f of 1 over n. Ln of 2 over n is equal to f of 2 over n, and so forth. So ln of 1 over n is equal to f of 1 over n, and you replace every occurrence of 1 over n with x. All right, so you found f of x, and you want to solve for the definite integral from 0 to 1 of f of x dx. So if you got to this point right over here, then you already got the answer. I didn't ask you to evaluate this definite integral, but we can evaluate it together. So first of all, the indefinite integral of ln x dx is x ln x minus x. You get that from integration by parts. And evaluating from 0 to 1, you get 1 times ln 1 minus 1. And then this is where it gets a little complicated. Normally, you would have minus 0 times ln 0 plus 0. But ln of 0 is negative infinity. So that's kind of complicated. And this is the reason why I didn't require you to solve for this definite integral. But if you want to solve it, all you need to know is that what you're actually trying to find is the limit as x approaches 0 from the positive side of x ln x. And if you remember how to solve limits using L'Hopital's rule, you can get that this limit is equal to 0. So then the final answer is, okay, so first of all, 1 times ln 1, ln of 1 is just 0. So the final answer is -1. All right, here's another practice problem. And here is the solution. So the first term in the series is equal to f of 1 over n. And then pi over n, that's the same thing as pi times 1 over n. So now you can replace every occurrence of 1 over n with x, and you get f of x is equal to the square root of 1 minus cosine pi of x. So the value of that series is equal to this definite integral right over here. And if you want to know how to evaluate this integral, you can check out the video on half angle identities, but I'm not going to go over it in this video. So now we're getting into determining volume and surface area. So the general method is to divide a shape into a number of smaller shapes and increase the number of smaller shapes to infinity. So we're going to determine the volume of a sphere. And to do that, we're going to determine the volume of a hemisphere. And to do that, we're going to divide the hemisphere into a number of cylinders. So this illustration shows how we divide a hemisphere into cylinders. So the red shape is the first cylinder. So this is the face of the cylinder. This is the side of the cylinder. And if this is kind of complicated, here's another view of it. Here's a 2D view. So the sphere in 2D would appear as just a circle, and each of the cylinders would appear as rectangles. And this length right over here is the radius of the first cylinder, and this right over here is the height of the first cylinder. And we're going to, this is called the disk method for evaluating volume, where you have like this x-axis right over here. And if you rotate the shape, this 2D shape across the x-axis, then you'll get a 3D shape. And then each of these rectangles, they just become cylinders. And then if you find the total volume of the cylinders, you can find the volume of the shape. So this method can be used to evaluate spheres and other 3D shapes. Now let's find the total volume of the cylinders. So the height of each cylinder is the same. The formula for the volume of a cylinder is h pi r squared. And since we're given that the height of each cylinder is the same, the height of each cylinder would be r over n, where r is the radius of the hemisphere and n is the number of cylinders. And now we need to determine the radii of the cylinders. So the radius of the first cylinder is this distance right over here. And so we have a right triangle where the hypotenuse is r and one of the legs is r over n. So we can determine that the radius of the first cylinder is the square root of r squared minus r over n squared. And for the second cylinder, we have a right triangle, and this time the hypotenuse is still r, but one of the legs is 2r over n. So therefore, the radius of the second cylinder is the square root of r squared minus 2r over n squared. And this continues all the way to the last cylinder, which has a radius of the square root of r squared minus nr over n squared. And we want to calculate the total volume of the cylinders as n approaches infinity. So that's this right over here. And so this is the volume of the first cylinder. So the height is r over n times pi, and then times the radius squared. So now we simplify. So first of all, we can factor out r, pi, and 1 over n. So it becomes this right over here. And we can also notice that we have square roots and squares. They all cancel each other out. All right. And then now we distribute. So r over n becomes r squared over n squared. 2r over n squared becomes 2 squared, r squared over n squared, and so on. And now we can factor out another r squared. So our series becomes this right over here. And now we can use the Riemann sum to determine the limit of this series right over here. So notice that this term right over here is equal to f of 1 over n, and this term is equal to f of 2 over n, and so on. All right, so we set the first term equal to f of 1 over n, and then we replace every occurrence of 1 over n with x. So now we've determined that f of x is equal to 1 minus x squared, and we need to evaluate the definite integral from 0 to 1 of f of x dx. So first of all, the indefinite integral of 1 minus x squared, that's x minus x cubed over 3, and evaluating from 0 to 1, that's 1 minus 1 cubed over 3, and then minus 0. So overall, it's equal to 2/3. All right, so we determined that this limit right over here is equal to 2/3. So we plug that into our original formula, and we get 2 over 3 pi r cubed. And this is the formula for the volume of a hemisphere. And to get the formula for the volume of a sphere, we must multiply by 2 to get 4/3 pi r cubed. And that is the volume of a sphere. All right, so now this is the final topic for today, which is other forms of the Riemann sum. So all the Riemann sums that we've seen so far are evaluated from 0 to 1, but you can evaluate it from other intervals. So you can evaluate it from 0 to a, and that's equal to this right over here, which you can prove by just by dividing the curve into n rectangles, and the width of each rectangle is a over n, and the heights, they are f of a over n, f of 2a over n, and so on and so forth. So for example, if you plug in a is equal to 2, then you get this Riemann sum right over here. All right, so this Riemann sum can be used to evaluate this infinite series right over here. So there are actually two ways to write this as an indefinite integral. So the first way is using the Riemann sum from 0 to 2. And the way we do that is we turn this into 1/2 times the limit as n approaches infinity. And we change this 1 over n to 2 over n. All right, and so now this right over here is the Riemann sum from 0 to 2. And notice that each of the corresponding terms are equal. So the square root of n over 2 is equal to f of 2 over n. And n over 2 is the same thing as 1 over 2 over n. And now we replace every occurrence of 2 over n with x. All right, so f of x is equal to the square root of 1 over x. So this limit right over here is equal to the definite integral from 0 to 2 of the square root of 1 over x dx. And then remember, we also had a 1/2 in front. So this is the first solution for this series right over here. And the second solution is to just imagine the n over 2 as n over 1 times 1/2, the n over 4 as n over 2 times 1/2, and so on. And now this time we use the Riemann sum evaluated from 0 to 1. All right, so that's this right over here, and each of the corresponding terms are equal. So the square root of n over 1 times 1/2 is equal to f of 1 over n. All right, n over 1 is the same thing as 1 over n. And we replace 1 over n with x. And then we determine that f of x is equal to this. So therefore, the series that we just saw is equal to the definite integral from 0 to 1 of the square root of 1 over 2x dx. So there are two ways to write the series that we just saw as a definite integral. And that means that, as it turns out, as long as you're familiar with the Riemann sum from 0 to 1, the Riemann sum for other intervals, such as 0 to 2, aren't that necessary, because Riemann sums that can be written as from the interval 0 to 2 can also be written as a Riemann sum from 0 to 1. So your priority should be to memorize and be proficient with the Riemann sum from 0 to 1. But if you're able to be proficient with that, then it's also good to memorize the Riemann sum for other intervals, because there will be some problems on the AP Calculus AB exam that will deal with intervals other than 0 to 1. But anyway, that's it for this video. So I'll see you all in video number 11.